Welcome to the deep dive. Today we're climbing the algebraic ladder way up, all the way to 8 dimensions, actually, to look at the Octonions. That's math BO-DO.
Right?
And this isn't just some, quirky math thing. It's a number system so wild it kind of breaks the fundamental rules of arithmetic.
It really does. But that exact flaw, that breakage, might just be the master key to unlocking some really deep symmetries in theoretical physics.
Okay.
So our mission, really, is to show you why mathematicians sort of had to sacrifice some core rules to even get to this 8-dimensional space.
And why that sacrifice is what makes them so important, maybe even central to understanding the universe.
Exactly. It's a fascinating trade-off.
So let's unpack this hierarchy then. You've got the real numbers, nice and familiar. Line them up, compare them, easy.
Then you jump to 2D, you add I, the square root of math 1, and boom, complex numbers, math BBC.
But you pay a price.
Yeah.
You lose ordering, right? You can't really say if I is bigger or smaller than 1 in a meaningful way.
Precisely. First sacrifice made, then comes the jump to 4 dimensions. The Quaternions, math BBH.
Hamilton, right. 1843, walking across that bridge.
That's the story. And he realized to make 4D work, you have to give up commutativity. The order you multiply in suddenly matters. So my best is just not the same as PERT.
Okay, so multiplication order matters now.
Yeah.
But associativity, like the grouping, that still holds for quaternions.
Yeah, exactly. ABPC is still equal to ABC for Quaternions. That part's safe.
Until the Octonions. The next step, 8D. And this is where the cost gets really steep.
It gets radical. Here you have to sacrifice associativity itself. The grouping changes the result.
That's the fatal flaw, isn't it? That's what really sets math apart.
Fundamentally. So that equation, ABC, PEC, it just breaks down.
Can you give an example like with the base unit?
Sure. So if you take 3 of the imaginary units, say $, E22, E3, you calculate E Tellery E2 first, then multiply by 3 Helter D dollars, you get E6 Eilers.
Okay, minus E6 Eilers.
But if you group it differently, E dollar times E2 A3 in A your Fowlers, the result flips sign completely. You get plus E6 ism.
Wow. Just changing the parentheses flips the sign. So wait, if the result depends entirely on how you group the calculation, doesn't that make them kind of useless for like standard calculations? How can you build anything reliable on that?
Well, that non-associativity has huge practical consequences. Think about matrices.
Yeah.
Matrix multiplication is always associative.
Right, yeah.
Since Octonions break that rule, you just cannot represent them with matrices. Not in the standard way.
Ah, okay. Unlike quaternions, which we use all the time in robotics, computer graphics, because they can be matrices.
Exactly. So this non-associativity kind of disconnects Octonions from that whole standard toolkit of linear algebra.
Okay, so they're algebraically weird, can't use matrices, sounds like a dead end. But the sources, they point to Hurwitz's theorem, saying this isn't just a flaw, it's like a defining boundary.
It's a hard boundary.
Yeah.
Hurwitz proved that there are only 4 of these special number systems, called norm division algebras, over the real numbers. Math BBC, Math BBH, and Math BBO. That's it.
What does norm division algebra mean, basically?
It essentially means you can measure the size or length of numbers consistently, and you can always divide by any non-zero number. That property holds for reals, complex numbers, quaternions, and octonions.
And that's the end of the line.
That's the end of the line. If you try to go further, like to 16 dimensions with the Sedenians, it all falls apart. You get 0 divisors.
Meaning you can multiply 2 non-zero things and get 0.
Right, which completely breaks division. So Math BO is the final, largest complete system of its kind.
So this boundary, this limitation, it's not arbitrary. It's a deep mathematical property. And because they're this final unique structure, they connect to other unique things in math, these exceptional structures.
Precisely. The symmetries that actually preserve the octonion multiplication structure, they form a group called G2
G22, okay.
And G92 is special. It's the smallest of the 5 exceptional Lie groups. Think of it like a very specific, very constrained way to rotate things, but it only works perfectly in 7 dimensions, which is closely related to the 8 dimensions of the Octonions.
And this is where physics comes in, right? This feels like where it gets really interesting. The dimensions themselves seem predicted.
It's kind of staggering, yeah. Look at the dimensions favored by superstring theory. 3, 4, 6, and 10 space-time dimensions.
Okay.
Now look at the dimensions of our 4 algebras. 1 for Math BV, 2 for Math BBC, 4 for Math BB, 8 for H for DN. The string theory dimensions are exactly 2 greater than the algebra dimensions. 1 plus 2, 3, 2 plus 2, 4, 4 plus 2, 6, 8 plus 2, D8.
Whoa, that's uncanny. It's like the math is laying the groundwork.
It's suggestive, right? And there's more. M theory, this sort of overarching 11-dimensional framework.
Yeah.
It needs to compactify the extra dimensions down to what we see.
Right, curl them up really small.
And often this involves using special 7-dimensional spaces. And the geometry, the structure of those spaces, it's governed by Octanion series, the Octanion symmetry group.
So the Octonians' unique math, their flaw, is literally baked into the structure needed for these advanced physics theories.
It seems deeply connected. The constraints in the math mirror the constraints needed in the physics.
Okay, mine's slightly blown, but it's not all theoretical physics, is it? Are there any, like, practical applications emerging?
Well, yes, actually. It's still niche, but people are using the Octanion Fourier transform, the OFT.
OFT. Okay.
Because Octonions are naturally 8-dimensional entities, the OFT allows engineers to treat an 8-channel signal, maybe like color video, plus 5 other data streams, as a single unified Octonion value.
So you process all 8 channels holistically at once using Octonian math.
Exactly. It's leveraging that unique 8D structure for complex, multi-channel signal processing. So not graphics, but data analysis.
Fascinating. So wrapping this up, we started with a simple idea. Keep extending number systems. This led us all the way to MathBOU, which had to break associativity, a really basic rule.
A huge sacrifice.
But that very flaw, that non-associativity, turns out to be the key. It defines this ultimate algebraic boundary, connects to exceptional mathematics like GT22, and incredibly, it seems tied to the fundamental dimensional structure required by string theory and M theory.
It really flips the script. The broken system holds the key. It suggests that maybe, just maybe, the deepest laws of nature aren't written in the simple associative algebra we're used to.
What if the universe operates on a grammar where the order of operations, the grouping, genuinely matters? That's definitely something to mull over.